agree on your screen as well. Okay, so it's a pleasure to introduce our speaker this week, Natalie Butterfield. So Natalie was an undergraduate here at University of Virginia. She graduated here 2011, we think.
Yeah.
Then she was a PhD student at the University of Iowa, including a REBA fellowship to the VLA or Socorro site. She was then a postdoc at Green Bank, where I think I first met you. You helped me acquire moonshine in Green Bank. I remember that, which was very nice. I still have some. And then you were a postdoc at Villanova. And about a year and a half ago, you rejoined the Charlottesville community at NREO as a scientist here. So we look forward to your talk.
Great. Thank you. So today I'm going to be discussing a recent survey. This was mostly some of the postdoc work.
Maybe just turn on your video so they can people can see you a little bit there. Great.
Okay. So most of the work that I'm going to be presenting on today was some of the postdoc work that I had done at Villanova. So this is some SOFIA, Hawk Plus, 214 micron polarization observations of the Galactic Center, called the FIREPLACE survey, which stands for the Far Infrared Polarimetric Large Area CMZ Emission Legacy Survey. So this was a large survey, a large project for SOFIA that was proposed by my advisor at Villanova, Dave, who is leading the survey, and our collaboration, several of whom are listed up here in this list. This work has been continued on by Dylan Perry, who is the current postdoc at Villanova. And so part of the work that I'll be presenting on today is some of the work that he's continued on this past year. Okay. So to start off, I'd like to paint the picture of a background of magnetic fields and galaxies. So to study this, I'd like to point to the SALSA survey. So this was a survey, a SOFIA survey that was led by Enrico Lopez Rodriguez, who has surveyed several nearby galaxies, also using SOFIA and Hawk Plus to study the magnetic fields in these galaxies. And so one of the things that has come out of this large survey that they have been studying is that the magnetic fields in these galaxies is really dependent on your viewing angle of these different types of galaxies. So when you look at face-on galaxies, so for example, the Whirlpool galaxy shown here, you can see that the magnetic fields seem to really trace the spiral arms and the structure of the galaxy themselves. However, when we look at edge-on galaxies, we see that the fields seem to be showing this type of poloidal field where you get the magnetic fields that seem to be oriented perpendicular to the galactic plane. And so when we go back to the survey of different galaxies that we can see here, we can see that this is true for many of these galaxies that are shown. You can kind of, it's a little bit harder to see in these LICs, but for example, here and in some of these other ones, you can see that the face-on galaxies, the magnetic fields seem to really trace the spiral arms, whereas when we look at these edge-on galaxies, so for example, M82 up here, especially towards the nuclei, you can see that the magnetic fields are predominantly perpendicular to the galactic plane. So what does this mean for our own Milky Way galaxy? What is the orientation of the magnetosphere in our own galactic center? So to understand this, we need to understand a little bit of background on the galactic center itself. So the center of the galaxy, which is shown here, is about the inner 200 to 500 parsecs of the galactic center. There's 10 to the 7 solar masses of dense clouds in this region, which means that you have a whole lot of potential for star formation. There's the environment in this inner region is really extreme compared to other regions of the galaxy, and is typically only found in other galactic nuclei and in nearby galaxies, or in early galaxies. So a lot of the properties that we observe in the galactic center are really extreme. So we observe denser molecular clouds, we observe warmer temperatures, we observe broader line widths. So it's a really dynamical environment compared to other clouds in the Milky Way galaxy and in the disk. Now, these clouds are thought to be organized into streams. So these streams you can kind of see here with some of these kind of larger structures. So you kind of see all of these clouds that seem to be oriented in this kind of infinity-looking shape, which you can kind of see traced by my cursor here. So when we looked at these clouds, spectrally, they seem to show kind of a velocity gradient that seems to connect these different clouds, which leads observers to believe that these clouds are connected in these types of streams. Now, the Orientation of these streams is largely debated. So over the last several decades, there have been several different models that have proposed how these clouds might be oriented or connected together. So are they two potential spiral arms, or do you have some type of connected, circular-like structure? Do you have some type of open orbital stream type model? So it is very, very heavily debated on the connection between these gas clouds, but there is this leading theory that these clouds are connected in some way. So the magnetic field, since this is a magnetic field talk, I would like to touch on some of the magnetic field properties. So these fields are thought to be much stronger than disk clouds as well, in the order of about hundreds of microgauss. And so here's kind of a nice diagram of that, or plot showing that by Yusuf Zadeh in 2022, where he looked at some of the NTFs, and I'll talk about that in a minute. He looked at magnetic fields in the center of the galaxy, tracing these yellow threads here, and measured what their magnetic field strengths are. And so you can see that the magnetic field strengths are higher than what we would expect for magnetic fields in the disk of the galaxy. So lastly, I wanted to touch on for magnetic fields is the idea between poloidal and toroidal fields in the galactic center. So when we look at magnetic fields in the radio, which are traced by these yellow threads here, we see that the magnetic fields seem to be poloidal in the sense that they are oriented perpendicular to the galactic plane. However, when we look at the magnetic fields in infrared using polarimetry, we see almost a toroidal field where the magnetic field direction seems to be relatively parallel to the galactic plane. So there's kind of this open question of what is the magnetosphere in this inner region? Why do we see two different types of field orientations depending on what type of wavelength or what part of the spectrum that we're looking at? So to go into a little bit of detail on some of the radio, so I'm not going to go into too much detail since that's not the main focus of the work that we were doing for FIREPLACE, but I would like to paint the picture of what the radio is showing us for the magnetic field structure. So this was the paper that came out of some of the Meerkat work. So this was Farhad Yousafzadeh's 2022 paper. And so what he did in this work here was to have a high pass filter on the Meerkat data where you can really see the NTFs showing up since they are very narrow threads of emission in the galactic center. So you can see all of these different threads showing here, which are tracing these magnetic field structures.
What's the resolution of the VLA data? Do you remember?
The Meerkat data?
Oh, it's Meerkat.
Yeah. So Meerkat is about 5 arc seconds or so. Yeah. Yeah, so these are the non-thermal radiofilaments, which we're also calling NTFs. Sometimes I've seen them referred to as NRFs, depending on who you talk to, but these are the non-thermal radiofilaments. So they have a falling spectral index, which means that they're synchrotron in nature. And since they're synchrotron in nature, what you have is you have a relativistic electron that's spiraling a magnetic field. So these are thought to all be tracing magnetic fields in the center of the galaxy. And you can see that predominantly they're oriented perpendicular to the galactic plane. Now, that doesn't mean that all of them are perpendicular. You can kind of see a couple that are out here that are oriented somewhat parallel. One down here that's a little bit parallel, a couple in here. But for the most part, predominantly, they are perpendicular to the galactic plane, suggesting that they're poloidal in nature. However, this is different when we look at dust polarization. So I would like to do a brief introduction on what dust polarization is, since that is the focus of what FIREPLACE is studying. So dust polarization is using polarized dust emission at infrared wavelengths. So what this means is that you have these dust grains, which are shown here in green, are spun up by nearby stars. So you have stars that spin up these dust grains, and then they're aligned with the magnetic field. So you have your short axis here, which is aligned in the direction of the magnetic field. So the infrared emission that we're seeing is polarized and acting as a screen. And so we're seeing that polarized emission perpendicular to the magnetic fields. And so this is the theory of BRAT theory, which is the radiative torque alignment theory for dust alignment. And so that is the technique that we're using to study magnetic fields in the FIREPLACE survey and using the HAWK+ receiver. I would like to mention that using this theory or using this type of method, you do run into a potential issue with polarized emission along your line of sight. since you are looking at or could be looking at multiple components along your line of sight, especially towards the galactic center. However, since most of the emission that we're studying or the clouds that we're studying are believed to be in the galactic center, and most of the emission, infrared emission that we're observing is from those clouds, we're thinking that a lot of the polarized emission that we're seeing is associated with the clouds in the galactic center. But I did want to raise that caveat that that is something that we have to be aware of, especially towards lower intensity regions in the galactic center. All right, so what does this look like for when we use this type of technique and study the magnetic fields in this inner region? So when we look at some of the large scale structures, so this is looking at this top figure here, which is showing the PILO 240 micron polarization observations, which was a balloon-borne mission studying the center of the galaxy. We see this large coherent structure, which seems to be relatively parallel. It's about 20 degrees relative to the galactic plane. There is a little bit of variation in these depending on what clouds you're looking at. Some that tend to be a little bit more parallel, some that might be a little bit tilted more relative to the galactic plane. But in general, we see a field that's about 20 degrees relative to the galactic plane. However, when we look at cloud-sized fields, so these are looking at observations that are on the cloud sizes, we see that the magnetic fields seem to trace the morphology of the clouds in the galactic center. So for example, this is showing some of the CSO 350 micron observations of the galactic center, where they targeted specific bright clouds in this inner region. So for example, we have SAGB2, which is located down here. We have the brick. We have the 50 and 20 kilometer per second clouds. And in general, what we see is that the magnetic fields seem to actually trace the morphology of the clouds. There doesn't seem to be this kind of coherent structure that we observe when we look at the larger scale gas structures in this region. So that raises the question of how are the cloud-sized magnetic fields connected to this large-scale pervasive field that we observe in this lower resolution type of observations. So to address that, we looked at, we used FIREPLACE, and this was the SOFIA Legacy project. It was initially intended to be a 2-temperature observation where we had a cool component, which was band E in the longer wavelengths at 214 micron, and then having a band C, which was 89 microns, tracing the warm dust, which is more towards some like H2 regions, to see how the magnetic fields may vary between these two components. Now, due to the closure of SOFIA, we were unable to get band C, so we were unable to get any observations at our warmer component. However, we were able to get a completed map of the galactic center in band E, and I'll show that towards the end of my talk. So we used this type of new or relatively new mapping strategy, which was somewhat different from previous observations. If I can switch back. So the previous observations towards several of these clouds used a observing method that was called chop-nod, where you basically chop between your targeted cloud, and then you chop somewhere off, and then on, and then off, and you go back and forth, and you do these on-off position switching on your interested cloud, which means that you're pretty much focused on just your cloud itself. You're not really getting the larger diffuse or the larger structures around your cloud. And so we used a novel method doing a Lissajous mapping strategy, and that's what this figure down here is showing. You can see the footprints of each of our different scans. So we had these long scans across our source, and then we slewed the telescope over, and that's what's being traced here by this yellow line. You can see the Lissajous pattern. And so this allowed us to trace across the galactic center and then have our offs be above and below the galactic plane there. And so because we had this mapping strategy, we were able to cover a much larger region of the galactic center. And so this is showing the footprints of what the first data release was targeting. So the first data release focused mainly on SAGB2. So that's the red, the bright red cloud, which is shown here in the center, and then some diffuse clouds or clouds that are associated or could be associated in the vicinity around SAGB2. So in this map, we ended up getting about 25,000 magnetic field pseudovectors in just this region of the galactic center here. And so this is all, I guess, discussed in the FIREPLACE 1 first data release paper. All right, so I did want to pause here and kind of do a inset showing the magnetic field, since it is a little bit harder to see in that larger image that I was showing, but it really kind of highlights what we were able to do with this survey. So here's kind of an inset showing the main clouds that are associated around SAGB2. And what we found is that in general, when you look at individual clouds, it still seems to follow a lot of the cloud morphology. We did a comparison with SAGB2 to previous observations for consistency to make sure that the observations of the pseudovectors that we were detecting matched the previous observations as well. And in general, they did. There was a couple that were slightly showed some slight variation in the polarization angles. However, that could be due to the different wavelengths that we're observing at, and the fact that you could be looking at different sections of your cloud, and therefore tracing different components of the embedded core of SAGB2. But in general, most of the pseudovectors that we're seeing trace the cloud morphology, similar to what was observed in those previous observations.
So when you say trace cloud morphology, I don't know if you're going to mention it, but so there's the fields are perpendicular in some regions, or parallel to filaments. Or...
So when I'm saying tracing the cloud morphology, so for example, I guess the best example that I could see is probably this cloud here. So you kind of have this kind of S-like shape here, where the cloud seems to kind of curve and have this type of structure here. And so what we see is that in the north, the cloud or the magnetic field seems to be oriented in this direction here. In this middle part, they seem to be oriented in this direction. We see a little bit of depolarization down here, and then in the down here, we're seeing the field tracing this direction. So it seems as if you're following the larger cloud structure.
So parallel to the filaments.
Yes. Yeah. So one of the key takeaways that we were able to do with the survey was to be able to do large sample sizes, or to do survey work with the orientation of the vectors and really understand their orientation and direction. So what we did was we took all of the 25,000 vectors that we had in our DR1, and we plotted them as a function of our polarization angle relative to the galactic plane. So 0 means that you have a magnetic field that's oriented parallel to the galactic plane. 90 plus or minus 90 means that you have a magnetic field that's oriented perpendicular to the galactic plane. And then we plotted these as a function of intensity, and then what their fractional polarization values were. And so what we found is that when we summed up how many vectors are associated in each 10-degree bin, we almost see this or this bimodal distribution, which is shown here in this top plot here. And so we see almost a 2-population distribution in the galactic center. So we see one that's oriented relatively parallel to the galactic plane, which is shown here around 0. And then we see the second population, which is oriented roughly perpendicular to the galactic plane. And so I would like to mention here that because we're looking at pseudovectors, which are headless, this plot is essentially wrapped. So when you go from plus 90, it wraps over to minus 90. So it might look like there's 3, but it is 2 populations because you have this wrapping due to the sign for your plus or minus 90 degrees. So could this be showing us that we have some type of poloidal and toroidal fields in the galactic center? Maybe, and this could be caused by shearing of fields by the orbital motion. And so to go over what that is, I would like to briefly mention, before I move on, I would like to briefly mention one of the things that we did want to look at was to see if this type of distribution, the bimodal distribution, was present over all of our different intensity bins. So we did break this up in terms of intensity bins. So the top is showing all of our 25,000 vectors, and then we broke it up into a high, medium, and low intensity bin. And you can see on this plot here what those are tracing in our field. So for example, the highest intensity bin is pretty much predominantly from SAG2, So you can see the yellow vectors there at the center. And then the red is tracing the sort of intermediate, which is pretty much most of the general clouds. And then we have the blue, which is kind of the peripheries of these clouds, or the lowest intensity bands. And the key takeaway here is that this bimodal distribution, which we had seen in that previous plot, is consistent, or is detected in all of our different intensity bands. However, when we get to the lowest, it's not quite as predominant as it was in the higher intensity bands. Now, the different plots here, just to briefly go over what this figure was showing, is we have our fractional polarization values shown here in plot A. Plot B is the same plot that I was showing here, but for each of the different intensity bands. Now, plot C is the plane of sky orientation. So if you plotted these vectors, how would they look relative to the plane of the Milky Way? So again, 0 is having a magnetic field that's parallel. And then if you had, plus or minus 90, that's having a field perpendicular. So it really kind of shows you how these would be oriented if you plotted these vectors on the sky. And then panel D is just showing if the vectors are more associated with being parallel to the galactic plane on this side versus perpendicular to the galactic plane on that side. So it's just a way of understanding or visualizing the orientation of these vectors relative to the galactic plane.
Question. So the galactic plane on your image is running.
Yeah. So it's oriented in this direction here.
And so the curvature that you see in the cloud, how much is that being traced? See, there's like a curvature there in the cloud.
In
In the overall, no, the whole image actually.
Oh, how you get this kind of
yeah,
tilt
right,
down.
right.
Yeah, so you do. So when you look at the clouds in, let me see if I can maybe go back here. So what we're seeing, so our DR1 pretty much covered this side here. So you do get this kind of like curving of the gas kind of towards this region down here. We don't, I guess, look at the clouds as like, what is the magnetic field doing in this particular cloud versus this one to see how that might be varying. And that is something that we've talked about doing, but it's how do you define an edge of a cloud? And so that's really the kind of the challenging part there, is to decide where you would need to make those cuts. And maybe that's something that we could do in the future where, if we wanted to do just like the highest or the red intensity bands, maybe we could have some way to kind of break up a cloud here using those type of vectors or something.
But the bimodalness is not caused by that curvature.
No, and it's something. So in a couple slides when I talk about DR2, that is one of the questions: is this associated with just how much dense gas we have in this region of the galaxy or the galactic center, or is this true over the whole CMZ? And we'll show that in a couple. Okay. All right. So okay. Oops. There we go. All right, so shearing of the magnetic fields. So is this poloidal and toroidal fields caused by a possible shearing of the orbital motion? So I had mentioned that we had this type of orbital stream-like structure where you had these gas clouds that are connected and thought to be orbiting around in the galactic center using, some type of orbital model, which is still heavily debated. But there's this idea that you have some type of primordial poloidal field direction, which is traced by the NTFs. And then as you have these gas clouds that are moving or orbiting around the galactic center, they could be dragging the magnetic fields with them as they're moving through this galaxy. This motion could then shear these fields into a toroidal type of field orientation. And that could be the reason why we're seeing a lot of the toroidal field direction in the dust polarization, which is heavily tied to these molecular clouds. Now, this also could be the source of the relativistic electrons that are needed to power the NTFs, which again is another open question for the Galactic Center, is where are you getting these relativistic electrons that you need to ignite the NTFs or highlight the NTFs. And so this could be where you're getting some of those relativistic electrons, which is shown here in my advisor Dave's paper from 2003. Now, this idea of this type of cloud shearing or poloidal and toroidal field, it's not a relatively new idea. This was originally proposed back in 2003. However, back then we didn't really have the large surveys that we had now to really investigate that type of question, or investigate that hypothesis. And now we can, using the large survey or data sets that we have with FIREPLACE. Oops. All right, so showing, I guess, the DR1 data set. So this was kind of our coverage that we had for the Galactic Center. It was, as I mentioned, predominantly on SAGB2 with a little bit of extended coverage, including some of the clouds that were around it. And so since DR1 only covers a small set of the CMZ, is that bimodal distribution relative of the whole CMZ, or is it just because we're targeting a lot of the brighter dust clouds in this region of the galaxy? And so what we need is DR2 to really investigate that. And here's showing the relative coverage between DR1 and then DR2, which includes the whole CMZ. All right, so the second data release, so this is the work that Dylan Perry, who's currently at Villanova, is working on. So the paper was submitted about a month ago and then uploaded to arXiv around the same time. So this is on the arXiv under FIREPLACE 3. So this is showing the full CMZ coverage that we had. And so for the second data release, we have about 65,000 pseudovectors across the whole Galactic Center. The top plot here is showing our Lysog patterns, so showing the coverage that we were doing, which had this type of X-like shape in order to get good coverage across the whole CMZ, including a lot of off positions that we could use, so you can see how far above and below the galactic plane that we go in order to get these relative off positions to do almost that type of chop nod work to do the data reduction here. But this shows all of the pseudovectors that we have, and you can see that the infinity-like shape, which we had seen previously, is still present in our full FIREPLACE survey. All right, so what we found, so one of the things that we wanted to do with the full data set was to check and see if that bimodal distribution was present in the full survey, or if it was something that was associated with the SAGB2 complex and all of the dense gas that we had in that region. So what we found is that we found similar results to FIREPLACE 1. The bimodal distribution or bimodal population was present in the full survey data set as well. We also looked at just the DR2 data set, so essentially looking at just this region, so not including DR1, to see if maybe those 25,000 vectors could be influencing some of the populations that we see here. And we do still see the same bimodal distribution, so that seems to be present throughout the Galactic Center, that you have these two populations. So one of the things that Dylan did for this work was to take it that extra step further and actually quantify this bimodal population. And so he fit the main population with these two Gaussians, one that is centered at about minus 82 degrees, and then one that's centered about minus 18, which is fairly similar to what the large population or the large scale coherent structure was that we observed in the PILO work that I had shown previously. Seems to be fairly similar to the population that he's measuring there. And then just to briefly mention FIREPLACE 2. So this was this also allows us for serendipitous results for some really interesting sources in the Galactic Center that maybe were either overlooked or were kind of overlooked in previous surveys, but really show up as an interesting source when you look at the magnetic fields there. And so FIREPLACE 2 was targeting one of these sources here, and if I have time at the end, I might touch on that a little bit later. Okay, so to wrap up, it's a little bit hard to see if these lights, but here's showing a nice LIC of the magnetic fields. So it's a line integral contour where you take the magnetic fields and you smooth them to this kind of continuous type of magnetic field shape or kind of overlay. And so here's showing what the magnetic fields look like for the FIREPLACE survey overlaid on the figure that I was showing previously. And so just to kind of wrap up some of the future goals that we're planning on doing for this work. So is there a connection between the NTFs and the dust clouds? We kind of raised that as, the poloidal versus toroidal fields at the very, very beginning of my talk. So is there kind of a connection between some of the clouds that we're observing and some of the NTFs? So when we look at some of these sources, so for example, here you can kind of see the magnetic field seem to be oriented in a similar direction. So that's for people online, that's this source here. We also see some, magnetic fields, pseudovectors, the FIREPLACE pseudovectors oriented in a similar direction here for this NTF. So we'd like to investigate this further to really see if there's a correlation between some of the dust clouds that we see and these NTFs. To take it that step further, like, could these clouds be providing the electrons that are needed to power the NTFs, similar to that diagram that I was showing previously? So is the magnetic field being sheared by the orbital motion of the clouds? So we showed that, you've got these clouds that are orbiting in the galactic center. It could be dragging the magnetic fields. So we want to investigate that further by looking at some of these orbital models and seeing if maybe some of these clouds, so for example, here you have the 20 kilometer per second cloud, and then you have this kind of tail end here. So could these clouds be sheared or dragged, dragging the magnetic fields during their orbital motion? And can that tell us or give us insight on the orbital motion of these clouds if we're seeing them sheared in a specific direction? Could that be, telling us the direction or the orbital motion of the clouds, and maybe give some insight on which of those different types of orbital models might be happening in the galactic center. And then lastly, could the field be influencing star formation in this region? Since we're looking at some of these collapsing clouds, which could be then forming stars. So could the magnetic field be influencing the star formation in some of these denser regions? I think am I out of time? Yeah, okay, perfect. All right, so then I'll end there.
Great, thank you very much. Thank you. Transition into questions and discussion. So if you're online, just raise your hands, and also here, people in Chalmers, that is maybe Maya can moderate if there are questions. Any questions for Natalie?
So I'm sort of not surprised you see a bimodal where you expect sort of a transition from parallel to perpendicular at certain densities. What is surprising is that you see a variation. You see that in all of your bins. So have you thought what's going on?
Yeah, so it is surprising that it's present in all of our different, regimes. So it is predominantly in the intermediate component. It's not quite as clear or quite as predominant in some of the lower intensity values. And then with the highest kind of intensity values, it's pretty much oriented parallel to the galactic plane. So
it is kind of with intensity with the densest regions aligned in the and we see on the Ian Stevens, we're doing this in the bones, these the large filaments in the galaxy, and we do see that where star formation is happening, that's not true. It's not necessarily aligned, so there is a lot of variation.
Yep.
This region is even more extreme. So
yeah, so one of the things that we've also talked about wanting to do would be to do, as I mentioned, looking at different lines of longitude to see how the field directions might vary as a function of longitude. So for example, one of the things in the most recent orbital model, so Diedrich's orbital model, is that you have these locations of close passage to Sagittarius star. And so in his, I think it was 2019 paper, you almost start to get, as clouds pass through their closest approach to the supermassive black hole, you almost start to get this tilt of the clouds where they start to almost rotate. And so we wanted to see if, okay, well, for example, if you're looking at Sagittarius B2, maybe you're seeing more of a tilt there, and you start to, it might be variable as you look at different locations along the orbital stream to see if maybe that could be somehow influenced. So there's a whole lot of possibilities that we could do with that.
Great. There's a question online from Gina.
Yeah, hi. Thanks. I think this kind of data is really awesome to see. I had two questions. One was, in the outskirts of your field, you find lots of vectors, and I'm curious whether those are real or just artifacts of the, calibration process.
Yeah, so we did have a lot of very stringent cuts on the data set. And so all of the vectors that are shown here are consistent with the conservative cuts for the SOFIA Hawk Plus data reduction. Now, I think that there are some interesting sources. So, for example, one of the ones that we see is kind of this clustering up here. And so when we look at that kind of clustering in this source, we see that those are actually associated with this kind of really high fractional polarization vectors down here, and are also associated with a supernova remnant that's kind of up towards that edge of the galactic center. But since it is towards the edge of our data reduction, and we don't have, and since we don't have that kind of cross pattern up in that region of our map, we don't really talk about it too much in the paper, since it is kind of, debated, like, could that be an issue with, the way that we are doing our mapping strategy and only having our scan in one direction and not the, secondary direction. So I think there are a couple sources in there that are worth follow up. I think I highlight some interesting sources that maybe are, could be followed up with, like, the JCMT or maybe some other polarization observations. But yeah, we do have to be a bit cautious about reading too much into those sources, just because, towards the edge of the map, the fidelity kind of goes down a little bit.
But you did have some low resolution balloon data.
Yeah.
So does it not? Can you check some of these low density regions?
So this one, I mean, your beam size is about 2 arc minutes. So it's not super great towards those edges. And I mean, you kind of can see some regions where you maybe have some type of influence, where you kind of get, some other sources where maybe you're getting kind of an averaging between the two within your beam. But yeah, it's I think you would need to do follow up with higher resolution, so like JCMT or something.
Okay. Yeah. And your second question, Gina?
I have another one. Yeah. Okay, I will. So the other one is, the Galactic Center is relatively far. There's other stuff in between. So, would there be a scenario that supports the same data, but you're not seeing anything from the Galactic Center because the magnetic field is so jumbled up that it doesn't produce polarization, and all you're seeing is foreground stuff?
So for some of the sources, so for example, in the PILO work, that is one of the things that they mention in their paper. It's a little bit vague. So they say that it's within the inner kiloparsec. Now, you can have the galactic bar in the inner kiloparsec. You can have, a lot of other types of dust lane features that are in that inner kiloparsec, which could be influencing them. So that is something that we have to be aware of. Now, especially for the brightest intensity regions, since most of the emissions, so for example, SAGB2, most of the emission that we're observing in this inner region is coming from SAGB2, that the polarization that we're observing is therefore associated with those features. Now, when you look at some of the lower intensity features, so for example, some of these clouds out here, maybe some of these sources out here, some of the peripheries, you could potentially have some type of line of sight confusion, because you might be looking at features that are at a similar intensity, and therefore, could be contributing to the polarized emission that we're seeing. But since a lot of these clouds, especially the red and yellow that are shown in this plot here, the dust emission follows the molecular gas emission, and the molecular gas velocities are similar to what we observe in the galactic center. Therefore, we're associating these clouds as being in the center of the galaxy, and therefore the dust that we're seeing from these clouds is associated with the galactic center. So the blue vectors, maybe that, you could run into some type of contamination, but with the red and yellow, we've compared the structures that we observe in our 214 micron with these other data sets, and these clouds are associated, or believed to be associated, with the galactic center based on their velocities.
Great. So perhaps just following up on that, are there regions where the meerkat orientations and your orientations, especially in the low density regions, tend to align? I think you mentioned what maybe.
Oh, yeah.
One or two places.
Yeah, I think I have a better figure here. Yeah, so we do see that. Actually, maybe what would be better is to just kind of zoom in. Yeah, and maybe that'll show up a little bit better. So on some of them, you can see certain locations where you get a similar direction in the magnetic fields between the dust polarization and the NTFs, but then you get other locations where it's almost completely perpendicular. So I think it is kind of an open question for some of these sources.
So the fields inferred from the NTFs is what?
The NTFs are tracing the field lines.
The
So they are the magnetic field structures, and then you have the relativistic electrons spiraling around them. So there are some where you start to see, you know, a very similar direction, you know, for example here, but then you get this other kind of like brighter source up here where it's almost perpendicular to it. So there's I think it's kind of, that could be almost its own paper, is investigating those and looking at individual NTFs and where you see a correlation and which ones you don't see a correlation, and what that can tell you about maybe the orientation of these clouds, or maybe what clouds they might be associated with, you know, this, because again, we could be seeing, you know, maybe this is actually a cloud that's, you know, in front of the NTFs or behind the NTFs, and it's not actually associated with them in that case. So I think, you know, it does require a very detailed analysis, which is further than the scope of the data release papers that we did here. But I think it is, you know, something worth investigating, since it is kind of an open question on, you know, how these things might be connected and what the magnetic field structure is doing.
Did you want to follow up?
Quick question. I know that in SAGB2, I believe it's Giles and Darren had papers about diachroic extinction being important in the farm-fred. Do you see a flip 9 degrees on SAGB2 in the deepest part?
So let's see, do I have any extra slides on that one? So what we see for SAGB2, and I guess maybe this would be the best way I can kind of zoom in a little bit. Yeah, so we see, I guess, this kind of curvature in it. I wouldn't say that we see like a 90-degree flip, but we see this kind of like almost curve, like a hook like type structure in the magnetic fields. And that seems to be fairly consistent with previous observations for SAGB2. But yeah, I wouldn't say that we see like a 90-degree flip in there. Yeah.
But are you seeing polarization holes then?
What do you mean?
Well,
like
so
polarization?
Yeah, so low levels of polarization in the dense. It looks like it.
Low there.
Yeah. So yeah, that is one of the things that we investigated in this paper, in the first DR1 paper, was looking at regions where we see high fractional polarization versus low fractional polarization. And it seems like in a lot of the really dense clouds, so for example, SAGB2, we see very low fractional polarization towards several of these sources. We also see that in cloud EF, which is thought to be kind of a younger version of SAGB2 and could be eventually forming stars, or may have some type of embedded star formation. We see relatively low fractional polarization in those regions. We also looked at regions where we see high fractional polarization. So for example, right around in here, there's several compact H2 regions, which is called G0.6. There's 4 compact H2 regions, and towards those H2 regions, we see really high, on the order of about 5 to 10% fractional polarization there, which could be an indicator that, again, you have these really luminous stars that could be spinning up the dust grains and then aligning with the magnetic fields. And so that was one of the things that we had investigated, was looking at some of these really bright H2 regions to see if those were associated with some of the high fractional polarization, and if that could be caused by this type of spinning of the dust grains caused by these high mass stars. So we investigated that towards some of these sources, and we did that in DR1. We didn't really do that in DR2 since the paper was already pretty long, but that is something that we wanted to investigate. So for example, in, if I have this here, so towards the 50 kilometer per second cloud, there's several H2 regions that are associated there. There's numerous other compact H2 regions throughout the Galactic Center. And so one of the things that we wanted to look at was to look towards those H2 regions and see if we also saw high fractional polarization, which could be an indicator that these dust grains are being spun up by those sources. So yeah, so to answer your question, we do see regions where we see low fractional polarization towards some of these denser cores, which could be caused by them being, the dust is really embedded, and so you can't have either, the luminosity or the starlight, penetrating the clouds to spin up the dust grains. You could also run into the issue of where you have possible multiple components, where you could see depolarization because you have some type of overlapping field lines towards those sources. So there could be other reasons why we're seeing depolarization in there, but there are several sources. For example, those two clouds, and then one of the other sources that we looked at, we also see a couple regions of depolarization in the source that we looked at for FIREPLACE too.
Now, let me ask, have you tried to quantify the field strengths yet?
So we did quantify the field strengths for this source here. So this was, so for FIREPLACE 2, maybe I can kind of show one of those figures here. So FIREPLACE 2, we did investigate the magnetic field strength, and I can jump down to this figure here. So we used the DCF analysis in order to quantify the magnetic field strength. And so for this source, what we ended up finding was an increase in our magnetic field strength towards where we're seeing kind of the brightest part of the ring, so this type of structure here. And so what we argue in the second paper is that what you're getting some type of feedback, either through maybe some type of cluster or some type of supernova remnant feedback that has been expanding and sweeping up the magnetic field lines, causing this increase in our field strength towards a radius of 4 or 5, which is kind of this region right around here, where you see this kind of ring, where we see a lot of this kind of brighter emission. So you could be seeing the magnetic field strength in there. So we have looked at the magnetic field strength for this paper. We haven't done it for any other sources, but there are numerous other sources in here that could be investigated in great detail, and we look into doing that further.
But that's in your plan.
Oh yeah, I mean there's just so much that we can. It's a really rich data set. So yeah, looking at some of these other sources in detail. I think one of our collaborators is doing currently working on SAG-C and doing some of the magnetic fields in there. But there are a lot of other interesting sources. Especially when you zoom in and you start looking at some of these different clouds, or looking at the LIC, you really see a lot of really interesting features that I think are worth follow up.
Any other questions? Ayush, please.
So if the bimodal distribution of the magnetic field orientations is due to the sharing of fields, does that mean this would be a feature that is universal across the central regions of all galaxies?
It could be. So let me go back to some of the salsa work. And maybe it'd be easier if I kind of zoom in a little bit. So here you can kind of see that in, oops, here we go. So M82, you kind of see this poloidal field here, and then you kind of see a little bit of a toroidal field maybe kind of off towards the edges. And so, maybe you're seeing kind of a similar feature where you could be having this type of either spiral arms or some type of orbital model or orbital motion, which could be dragging them. And, if your orbital, clouds are very narrow, where it's only looking at a small portion of this, and most of the, above and below the galactic plane is this type of poloidal field, you could be kind of getting a similar situation. Now, I think you would almost need to go really high resolution in order to start to see that type of, differences or variations within the clouds, or to be able to resolve, maybe that narrow orbital stream within those galaxies, in order to differentiate between the two. But yeah, I mean, especially since, a lot of these clouds or galaxies are showing a somewhat similar feature there, we could be seeing a very similar, feature in those galaxies. But I think you would need to have high resolution in order to confirm that.
Has there been any ALMA polarization work in any of these clouds you've compared to?
So there has been some. There was a recent and actually active ALMA polarization project for SAG-B2 to look at some of the compact sources in there, and maybe to tie it into the almost FIREPLACE survey to see how the magnetic fields might be compared or connected to the compact sources. I don't think that has currently gotten any observations yet, but it's active this cycle. I think there's also an active project, or last cycle there's an active project for doing SAG-C. So there's a couple ALMA projects that are looking at some of the really kind of brighter sources. And here there was, I think, also one that looked at Sagittarius Star, of course, doing the supermassive black hole, looking at some of the fields around that. Yeah, there really hasn't been a whole lot, mainly just because the polarization for ALMA, that was cycle 8. That is somewhat relatively new, and then doing the data reduction, kind of takes a little bit of time. So I haven't really seen too much come out yet on those, but there are a couple on the horizon. So it'll be interesting to see how those compare to some of the FIREPLACE work, and how, those regions where we see, maybe depolarization, maybe that's just because you have, a really complex field that's below our beam size for FIREPLACE, and therefore you're almost getting depolarization that way as well. So.
Great. Paul, you have a question?
Yes, first, thank you, Natalie, for the talk, and I think this is really amazing data. My quick question essentially is based on the bimodal distribution in magnetic field orientations. Have you ever think about to compare with certain model, because we think that in 3D this whole galactic disk could be kind of tilted with some inclinations. So, and if you're very edge on to very face on galaxy, you have probably some dominant preferred orientations. So could this actually compare to certain model prediction, then we can get some idea of this inclination of our galaxy?
Maybe. So in regards to your question about doing almost a 3D type of analysis, we've thought about that a little bit with some of the clouds. The main way that you would get the kind of line of sight magnetic field component is doing Faraday rotation, and that's looking at the at the radio wavelengths. And so you kind of get that maybe towards some of these sources where you get this kind of potentially the orientation of the NTFs to get that line of sight of is it tilted towards you or is it tilted away from you. One of the clouds that we wanted to investigate in detail, which was this source down here, if I can switch over to the radio. So one of the sources that we observed, the ring, which shows that ring-like structure in the magnetic field, in the Meerkat data, it does show some synchrotron emission, especially when we looked at this in the spectral index work from that paper. You kind of see this falling spectral index, which suggests that the emission that we're seeing there is synchrotron. And if it is, then we could be able to measure the magnetic field strength and do some type of Faraday rotation on that diffuse structure to see how the magnetic field might be oriented along our line of sight, and to then therefore be able to do some type of 3D analysis of the magnetic field, at least in this region of this source. Now, we did run the specs. We would need a ton of time in order to do that type of analysis, since the emission is relatively faint. In the Meerkat data, it's really faint. And then in order to get down to like a 1% fractional polarization, which some of this emission could be, we would just need a ton of time. And so it's not really feasible with the VLA right now. But we might be able to do that with maybe either Meerkat or potentially doing that with the NGVLA. So that is something on the horizon that we would like to do, would be to somehow be able to get the line of sight orientation of the magnetic fields to really paint the picture of how the magnetosphere is oriented, and if there could be this tilt, either towards us or away from us, or how that is oriented.
It's almost been one also too much time.
So I mean,
high up in frequency.
Yeah, it might be a little bit high up in frequency. So we looked at so the VLA 5 gigahertz and ATCA 25 gigahertz. We don't see the ring there, which could be either due to sensitivity or it could be due to the fact that you have this falling spectral index. Now, with Meerkat, it was only like over 1 gigahertz of bandwidth. So, your spectral index error bars are really high at that point because you're only looking over, 1 gigahertz. So it is kind of a toss-up on what the radio observations are doing. Now, Betsy Mills has a recent VLA project to look at ammonia and do 25 gigahertz using the VLA with higher resolution and better sensitivity. So we want to check and see if maybe any of these sources are associated there. You can kind of see, they have these two kind of little compact sources there, which, could be these features here. And you maybe have something up here. You may have some type of, extended emission, especially towards some of these, this part of the ring here, which kind of shows a somewhat slightly flat or slightly falling spectral index. So we might be able to get some, radio data from that part of you know, the cloud. But yeah, I think following up with the radio observations just to be able to fill in this part of the spectrum, I think is essential. And so ALMA might be a way to do that. Yeah.
Before we end, can I come to the question of the influence of the field on star formation? As you know, most star formation is in SAGE-B2. There's very little in the brick, and there's some in SAGE-C.
Yeah.
I don't suppose you could zoom into your big map that shows this. We can do DCF by eye. And just show me how ordered the fields look like in the brick, or disordered in SAGE-B. You know, are they disordered in SAGE-B2, suggesting weak fields? Are they ordered in the brick?
Yeah, maybe this one would be a little bit better. If I can a little bit better. Yeah, they're pretty well organized. I mean, a lot of the nearby ones, nearby vectors seem to be relatively organized. We do see regions of where you might get depolarization, which again could be that you're getting a
SAGE-B2, is it there?
SAGE-B2, yeah, is right here.
And then brick?
The brick is right here. And so that one also shows, it's very similar to Thashara's slides where she saw the, you know, kind of the similar curvature of the brick. But yeah, we don't really see a lot of, you know, kind of twist or like, you know, 90-degree rotation of the magnetic fields in those regions. And for the most part, in a lot of our sources, you know, the magnetic fields seem to be relatively aligned. I mean, when you get some of these sources where maybe you get a cloud that's kind of overlapping between them, that you start to get, you know, one that's almost this direction, and then, you know, a couple over, you kind of get a
the Pli DCF in SAGE in the brick was basically milligauss, you know, quite strong fields, even though there's this global curvature. And then SAGE-C, quite interested in SAGE-C.
Yeah, so for the most part, so we have, you know, we do kind of get this, you know, almost 90-degree kind of, you know, where a lot of these fields seem to be oriented perpendicular to the galactic plane, and then as you get up here, you're kind of going a little bit more parallel to the galactic plane, and then these are almost like 90 degrees, or sorry, 45 degrees.
I mean, Ruben can correct me, but I think in our James Webb images of SAGE-C, we have this almost like a hatched cross pattern of bracket alpha, which might indicate, you know, some kind of bimodal distribution, but maybe it's also showing up here.
Yeah.
Great. Any last questions for Natalie? Okay, if not, let's thank Natalie again.